All right, we should be recording. This is the first part of chapter 6. This is going to be 6.1. But just to give you a heads up, chapter 6 is linear programming and the simplex method. We'll do the same fashion with the PowerPoints here. And in the upper part of the screen, you'll see just a little notepad with whatever notes I have. So 6.1 is the table method, an introduction to the simplex method. It's pretty much quick and easy to go about doing things that way. And 6.2 will be the simplex method, the maximization with problem constraints of the form less than or equal to. And then 6.3 will do the dual problem. And it'll be minimization with the problem constraints of the form greater than or equal to. And then finally 6.4 will be max and mins, but with mixed problem constraints. So without further ado, we'll get into 6.1, which is the table method. It's very similar to the geometric method in the approach that we're going to make basically a table that we'll solve our solutions with. So the first thing to talk about, I'll just move this a little bit out of the way right here, is the standard maximization problem in standard form. So when we talk about standard form, basically all we're trying to do is talk about how we want to display basically this maximization problem or this linear programming problem. So just to use a common example that we had before, just to jump ahead to the next slide, just to show you. This is the one where we did with the standard tense and the expedition tense. So I'm going to rewrite this. I'm going to have a max, and I'm going to profit maximize, and then I'm going to have 50, and I'm going to call it x1 plus 80 x2. So I note that I'm going to get rid of my x and y because we're going to be able to do it with a lot more variables in this case. Again, this is called my objective function, and I should have just wrote an objective, but I'll abbreviate that. So you have objective, and then x1 is going to be defined as the number of standard tense, and x2 is going to be defined as the number of expedition tense. I'm sorry if it's a little sloppy. It's still on the PowerPoint, so you can see it there as well. I'm just trying to make sure you guys, again, or incorporate that this is the decision variables. Right, so that's how we decide which variables we're going to maximize or operate with. So we have that. And then we're going to have our basically problem constraints. And a lot of the time, we'll just call that subject to. As you can see over on the far right of the PowerPoint, you'll see subject to, and you see the constraints. So in this case, we first had our cutting constraint, and then we had our assembly department constraint. So in other words, x1 plus 2x2 is less than or equal to 32. And the other constraint was 3x1 plus 4x2 is less than or equal to 84. And this is the assembly department, the number of hours available. And again, we need to keep in mind the non-negativity constraint, as we would call this. x1 and x2 must be greater than or equal to 0. We call that the non-negativity constraint. So those are the pieces of information that kind of should be familiar for you guys and you've seen before. But let's go back up one slide before this. So this is basically that standard form. This is how we write up all these, right? We might write the maximum, the objective function. As you note here, it says profit, then it has coefficient variables in front of each of the variables, if you will. So in other words, this is probably the, if it's profit, this is how much money you make off of each X1 units that you sell. And this is the profit you make for every X2 units you sell, and all the way up to XK units of basically the profit. You can also have a cost function as well, you'll find out later, but needless to say, this will be subject to problem constraints of the form of A1 times X1 plus A2 times X2, basically coefficient in front of the variable, right? So in other words, this is what maybe amount of hours, if we're thinking about the hours constraints, this is less than or equal to the total number of hours available. And you notice that hours must be positive, right? Then we have the non-negativity constraints. What we were saying about mixed constraints and greater than or equal to constraints, that'll be when we do the cost, which will be in 6.3 when we do the dual problem. But don't worry about that just yet. So this is basically the standard form. So just like I said, this should look familiar. This is our constraints that we've had before, which is pretty neat. So we had the basically company who's going to make standardized tents and expedition tents. They have a profit function where they get $50 for every standard tent and $80 for every expedition tent they sell. We went and found the answer for this already before, but it'll be good for us to go and show how to do it with the corner table method. So one of the things that's cool though about linear programming is we're now going to introduce things called slack variables. The idea is that they take the slack out of the inequalities. So for example, I'm going to make this a little bit bigger for you guys. This right here and this right here are considered inequalities, right? And we'll call those the I system. I'm not too big on the terminology in terms of I system and E systems, but it's the terminology your textbook's going to use. To me, you probably know that those are inequalities. And we'll know that when we talk about making them equalities, then they would be called the E system. Basically, what you do with these is you're going to add something called the slack variable. So in other words, the x1 plus 2x2, we're going to add s1 to it. And then that's going to make this bind instead of being less than or equal to. So in other words, it makes the constraint binding. And that's why it takes the slack out of it, okay? And that'll be the same for the other ones. We have 3x1 plus 4x2 plus s2. Notice it can't be s1, it's s2. It's its own slack variable for the other constraint. So equals 84. Again, took the slack out. Hence why it's called a slack variable, right? So that, and it's also on this PowerPoint slide, so you can see that there too. I just get so used to writing this out, but slack variables. And I'm sorry if that's a little small font, but I think you guys can see from also the slide that we're on. But okay, so some terminology for understanding the table method. Basically, we talk about the inequalities are called the I system, right? Inequalities are these parts. And then we have the equalities, which are called the E system, this part, okay? And then we'll talk about expanded coordinates. Expanded coordinates is basically like right now, if you're thinking about this, you just tell me this is x1 and x2, right? But in expanded coordinates, we'll actually talk about it for, I'll write over here. The regular coordinates would be x1 and x2, right? And then you put a parenthesis there. But now we're gonna have s1 and s2. So in other words, we have all of those variables that are considered in there because we introduced slack variables. So you might be wondering, okay, so how do we make a table with this? And so I'm going to minimize this so we can just focus on the table. The idea behind the table is that you're basically going to make a table. And here, actually, we're going to make this up, but I'll put it down here. I think you guys can still see my handwriting and all that. So if we're going to make a table for basically this problem, what we want to do is we put all of the variables in the table. So you notice I have x1, x2, s1, and s2. Those are all the variables that I have in there. Now, what I need to do is basically pair off zeros with each of the systems. So the way that the algorithm for the procedure starts is that you pair x1 and x2 to have zeros together. Then you pair x1 and s1 to have zeros together. Then you pair x1 and s2. Then you move, now that x1 has been paired with everything with a zero, then we move to x2. Well, it looks like s2 must be paired with s1, and x2 must be paired with s2, and then finally s1 and s2 must be paired together as well. Now you might be wondering, how do I find out what these values then are? Okay, so you're gonna have to go through and solve each of these for the systems. So in other words, for the first one, we have x1 and x2 equal to 0. Move this up just a little bit. That means you're going to have this variable here, x1 plus 2x2 plus s1 equal to 32, and 3x1 plus 4x2 plus s2 equal to 84. And in this case, what we need to do, in order to do number one, we need to put in the zeros. So that means it'd be 0 plus 2 times 0, right? Because x1 is 0, and x2 is 0, so that's why 0 is there as well. We have plus S1 equals 32. Well, that seems obvious that S1 is what? 32. That wasn't very challenging, right? So the other one will be 3 times 0 plus 4 times 0 plus S2 equals 84. Well, that's really easy as well, right? That's just 84. Okay, they're not all that easy. So let's check out this number 2 one. It's a little different. So in number 2, so basically all we're doing is we're filling in the table with all the values. And then once we have all the tables values filled in, we're going to go back and put that into the profit function. And I'll show you how all that works. So in 2, we know that x1 equals 0 and s1 equals 0. So we need to go put that into all of the formulas that we have, or all the equations. So if we go through and put that in there, we'll have basically 0 plus 2 times, well, it's just x2 still, because we don't know x2. But we do know s1, which is 0 equals 32. So that means x2 equals, well, 32 divided by 2 is hopefully 16. Make sure that I did that right. I believe that sounds right to me. So 16. And then we got to put the other ones in. So the second part of this, the 3x1. So 3 times 0 plus 4 times, well, we know it's 16, right? Plus s2 is, well, we don't know what s2 is, so we got to put that in there. 4 times 16 is 64 plus s2 equals 84. We move the 64 to the other side, we'll end up getting 20. And again, you should verify that you know how to do this on your own as well. Sorry if that was off the screen a little bit there. But, okay, let's pick one maybe that's a little harder. Like, for example, actually, let's do one more just down the line. So let's do number 3. So we're going to do number 3-1 as well. So in this one, x1 is equal to 0 and s2 is equal to 0, okay? So we have those both equal to 0, so we're going to plug those in. So we have 0 plus 2 times x2 plus, oops, we don't know s1, is equal to 32. So we don't know x2 or s1, so we got to just go to the other equation. So we have 3 times 0 plus 4 times x2 plus s2 is 0 is equal to 84, right? Okay, so that means x2 is equal to, divide both sides by 4, that would be 21, I believe, right? Yeah, 21, again, verify if that is correct. Now we go back and put this in there. So we have, I'll move the slides up, 2 times 21, right? I'm putting this into this equation now that we know x2, plus s1 equals 32. If I go and solve this, I think this is 42 plus s1. If I move this the other time, I get s1 equals negative 10. Okay, one thing that's important to note is that when we introduce these slack variables, the slack variables must be greater than or equal to 0 as well. If they are negative, that is not a solution. So this is not a feasible solution. So we would cross that out, okay? So let's go through, and I'll just fill in the rest of the table. You should pause right now. Actually, let's do 6 together, because I want to make sure you guys understand how to get 6 as well. So in the 6th one right here, we have basically s1 equals 0 and s2 equals 0, which means we basically have x1 plus 2x2 equals 32, and we have 3x1 plus 4x2 equals 84. Okay, you might be like, oh, well, that's just simple. We can just solve that using matrices and do reduced row echelon form, right? And then we get the solution for that. That's one way you can solve it. You can also do the inverse matrix of the coefficient matrix times the constant matrix, just like we did in chapter 4. So review that if you are at all unfamiliar with it. We're going to be using it a lot, and you're going to have a lot of these problems that are going to have more than 2 variables. In fact, if you look at step 3, it says use Gauss-Jordan method, or another method if you find it easier, right, to solve those variables, okay? So here, I'm going to fill in the table. You should pause and go through and do this real quickly to make sure you understand. If you don't do it on your own, and then you have to do it on your own later, you might panic. So I would make sure you understand how to do it on your own. All right, so I got negative 12 for here. So that means, again, this is not a feasible. These are infeasible solutions. And what's going to be cool here is when I show you this on the XY plane or the graph, you'll be like, oh yeah, that makes sense why it's not feasible. So, and the next one's 28, 0, and 4 and 0. And then we have 20 and 6 and 0. All right. Now, the next thing we need to do, so I'm going to click ahead on the next slide. So it looks like this is our table that we have. Now, we want to put in this, we want to put in this profit over here. And then what we do is we just plug in the x1 and x2 variables in there. And so that's why the profit's 0 here. So we just plug 0 in for x1, because that's what it equals here. And x2 equals 0, so we plugged it in here, so that's why it's 0. We get 1280, and we get 1400 for these, and 1480. Make sure you understand how to get that, right? That's the 20 goes in for the x1, so 50 times 20, right? And then plus 80 times 6, which gives us the 1480. And that should look familiar. That's what we found earlier before, okay? Now, Theorem 1 here is if the optimal value of the objective function in linear programming exists, then that value must occur at one or more basic feasible solutions. So this is one of the basic feasible solutions. That's actually what 1, 2, 5, and 6, they are basic feasible solutions. And the optimal solution actually occurs at the point 20 and 6. Now, let's show you, oops, oh, I don't have the graph. Let's go previous. Previous. Now, you might be looking at this graph, and I want to show you this because I think it's kind of neat. So we just said, I'm gonna make my view again bigger so that way I can point to the solution table that we have drawn up here, right? So this first one, we had x1 and x2 equals 0. So we look at our graph here, that's this point right here, right? The O, or the origin, right? That next one we have is 0 and 16, right? Well, that's the point A, and that is in the shaded region, right? It's on the line, okay? Now the next one that we have is the point 0 and 21, which I crossed out already because I said it's infeasible. It's not in the feasible region. If you look at our table, you'll see, or not our table, sorry, our graph, you'll see that point D is 0, 21. You'll notice that it is not in the feasible region, hence why it's considered infeasible. And that's why the slack variable is negative, to try to bring that down to the feasible area, but it doesn't work that way. You can't do that, all right? And then if you look at the point 32 and 0, that's point E, which is also infeasible. It's outside of the feasible region. Kind of neat. And then 5, you have 28 and 0. Well, that's point C, 28 and 0, which is a feasible solution. And then finally, you have the optimal solution, which is that 20 and 6, which is point B. Kind of neat that you can see it now with a graph too. Now, when we move to higher dimensions, it's harder to see that, right? Because basically 3 dimensions is as far as we'll go, and then you can't really do 4 dimensions right now. So at least in this class. All right, so let's do a match problem now that I've introduced this new concept to you. So I'm gonna put this, I think right here. Yeah, that'll be good. All right, so I'm gonna move my scratch paper over to the next page. All right, so we have the matched problem. I'm gonna try to straighten that out. Number 2. So let's write down all the information we have. We have the max of the profit of 30x1 plus 40x2, subject to 2x1 plus 3x2 is less than or equal to 24, and 4x1 plus 3x2 is less than or equal to 36, and we have x1 and x2 are greater than or equal to 0, non-negativity constraint. Now, if we introduce our slack variables, right, which is basically how we would do slack variables. Probably wondering why I can't draw on a line instead of drawing through the line. But I'll write down here, we have 2x1 plus 3x2 plus s1 equals 24. So, right, this is the I systems, the inequality systems, and now I'm going to make them E systems, if you want to follow along with the terminology in the text. Plus S2 equals 36, okay? So we got that. Now all they need to do is make a table again. So if we make our table for it, all right, we'll move this up a little bit. If we're making our table, we're gonna have table x1, x2, s1, s2, right? I'll draw my lines. So I'm gonna pair x1 and x2 as 0 first, then x1 and s1, then x1 and s2, then x2 and s1, then x2 and s2, then s1 and s2, right? So again, I'm gonna have basically 6 systems I have to solve for, right? 2 of them will probably drop out. So let's fill in those zeros. Why don't you pause the video and fill them in yourself and see if you can get them, okay? So take a chance, maybe pause it right now, and I'll fill in the numbers real quick. 24. I guess I could pause the video and then just have it display back up to you. I think this is -12. Let's check that one because I have it scratched off on my paper here, but. All right, so hopefully you got those numbers. If you didn't, this is a great question to ask me during the office hours. Okay, let's put that profit function over here. We have 30x1 plus 40x2, all right? So we're just going to basically plug those in. So in this first one, I'll have 30 times 0 plus 40 times 0, which is 0, which, yeah, seems obvious, right? Now the next one I would put in 30 times 0 plus 40 times 8, which gives me 320. And then since this one has a negative 12 for a slack variable, because right, when we introduce those slack variables, they need to be greater than or equal to 0 as well, right? Because basically if you made them really negative, then you can make x1 and x2 really, really, really large, right? So keep that in mind, all right? So that means no solution there and no solution there as well. Now, as the next one, we'd have 30 times 9 plus 40 times 6, which gives me 270. So far, 320 has been my largest number. So if I was operating this, I'd probably do 0 and 8. But I still got to do this 6 down here, and I have a hunch this is probably the largest amount. Oops, 40 times 4. That's equal to 340. So that is our profit maximizing value. In other words, we want to have x1 be 6, x2 be 4. Now, let's write this in expanded notation. Expanded notation, again, is x1, x2, s1, and s2. So that means this value would be 6, 4, 0, and 0. If I wanted to say this one right here in expanded form, this would be 12, 0, 0, and negative 12. Not 71, but 72, but negative 12. Looks like a 7, but it's a 1. All right. So that's expanded form. You will be asked how to do that in the future, just so you know. Like all of this stuff that I'm talking about, right? Obviously. All right. Let's go on to the next one. So in this next one, you notice, I have 3 subject to constraints now. So let's go through and fill this one out as well. So in this one, I'm gonna move my paper up and I'll make this bigger again. And you guys should recopy the problem down on your own. Make sure you have that. And I'm gonna use a different color so that way the black doesn't look like it's the same problem. So again, and I'm sure the blue looks the same color as the black. So we'll call this the match problem number 3, okay? And I'm just gonna, I'll write all of it down again. I was gonna shorten my steps, but we'll have our profit function, 36x1 plus 24x2, subject to the following constraints. Put that up a little bit. X1 plus 2x2 is less than or equal to 8. And x1 plus x2 is less than or equal to 5, and 2x1 plus x2 is less than or equal to 8. And x1 and x2 are greater than or equal to 0, right? The non-negativity constraint. Now what we need to do is add our slack variables again. So I'm going to try to move this over again. And so these are our I systems, right? And now we're going to make our E systems. In other words, inequalities and equalities by adding the slack variable. All right, so that means x1 plus 2x2 plus s1 is equal to 8. And then I'll have x1 plus x2 plus s2 is equal to 5. And then I'll have 2x1 plus x2 plus s3 is equal to 8. So in other words, now I have 3 slack variables. So when I go and make this table, right? And so I'm going to jump and just put the table solutions on. But I'll put them up here real quick, and then you can pause the video if you want to write them all down. And then let's talk about how you solve one of them, because I think this might be a good chance for us to go through again. And so like this would be our table that we'd have. I'd have, right, this is our constraints right here. We add our slack variables in, right? 3 equations, so 3 slack variables. And so we go through and we put them all in. We have x1, x2, s1, s2, and s3, and we go through and solve all of them. And as you can see, a couple of them are dashed out because the slack variables are negative, which means they're infeasible. And if we're looking at this, this is going to be our optimal solution right here: 3, 2, and 1, and 0 and 0 for our slack variables. Okay, so let's show how we can get maybe let's do this one. Let's do that one. We'll do this. Let's do this one right here. So in other words, we know S1 and S2 are 0. So we'll solve that just so that way. So just to show you again as a reminder, I'm sure you guys, S1 is 0 and S2 is 0. So if we know that, and so that would be the, if you had this on your table, 8. It would be the 8th one down in your table. I think you should have 10 in there. So that means if we put those in, we have x1 plus 2x2 plus 0 is equal to 8. Would be that one, right? If we plugged in that S1 equals 0. Hold that steady. And the other one would be x1 plus x2. Oh, S2 is 0, so that's equal to 5. And then I have 2x1 plus x2 plus S3 equals 8. Right now you might be thinking, oh man, I have 3 equations and 3 unknowns. So there's 2 things you could do. You could either solve this real quick, right? Or you could put it all in as a matrix and do the Gauss-Jordan elimination method. And so that's what I'll do real quick, right? So go to your matrix, go to edit, let's say A, and it's got to be what? 3 variables. So that means we're going to have 3 rows and 4 columns. So 3 by, whoops, not 34. 3 by 4. And we just put those values in there. So we'd have 2, 0, and 8. Why does this one have 0? Because S3 is technically the 3rd variable column. Okay? And then we'd have 1, 1, 5, or sorry, 0 and 5. And we have 2, 1, 1, and 8. So your matrices should look like that. Again, that first column is your x1, second column is your x2, third column is actually your S3, and this one is finally your number column. And then we just do second quit, and then we go back to the matrices, and we do math, and then we go to reduce row echelon form, and we put in that matrix A, and it spits us out the answer. So x1 is 2, x2 is 3, and S3 is 1. So we just put that into our table. So that's how I got this value right here. So just so you guys know. Okay, the next thing, the last thing we need to talk about before I cut the video off is what are non-basic variables? The value is 0, and the basic variables, the value is something else. So for example, in the above one here, when I talk about, so the above right here, we have 3, 2, 1, 0, and 0. So the non-basic variables are S2 and S3 because they equal 0, and the basic variables are X1, X2, and S1. By the way, this is never meant to be shown. This was my notes for when I lectured, but it's sometimes a little quicker than I think me writing it all out again. But for example, if we were to pick like one of those solutions, so let's say we have the 0, 0, 8, 5, and 8, which is the first initial solution on the table. If you were to go and solve your table like this and put them all in. By the way, you should pause the video and make sure you fill out this table on your own, okay? It's good for you guys to do that. Oops, back up. So in this case, my non-basic variables are x1 equals 0 and, whoops, and x2 equals 0. And my basic variables are S1 equals 8, S2 equals 5, and sorry, S3 equals 8. So, oh, you can't even see that, I'm sorry. So, non-basic, think of the values are equal to 0. Basic, they're equal to some number, okay? Pretty straightforward, pretty simple, but they can be confusing. I usually remember non-basic has an O in it. So I think zeros, that's how I remember it when I was first learning it a long time ago. Okay, next slide. This is just in summary. So summary of what we basically did in more technical terms, right? Step 1, use slack variables. So you introduce slack variables to make the I systems become E systems. Step 2, form a table, right, with all the variables. Step 3, fill in the table. Use Gauss-Jordan elimination method whenever you need to, right? If systems has no solution or infinitely many solutions, do not complete the row. And finally, step 4, find out which one is the profit maximizing value. So pretty straightforward there for section 6.1. So if you guys have questions, let me know. And there you go.